In this video, I'm going to show 4 different experiments we did in class to explore resonance and how energy moves through different systems. Each experiment shows resonance in a slightly different way. So let's jump into it. So first, we worked with a spring and a hanging mass. Instead of pulling the mass directly, we moved the top of the spring up and down at different speeds. One important thing we noticed is something called phase lag, which is basically how delayed the mass is compared to our hand. When we move the spring, the mass doesn't respond instantly, it falls slightly behind. That delay is the phase lag. At the right speed though, the system's natural frequency, we reached resonance, where the motion got much bigger because energy was being added at the perfect time each cycle. Kind of like pushing someone on a swing at just the right time. As we started changing how fast we moved it, the lag changed too. The faster we drove the system, the more the mass lagged behind our motion. And when we went too fast, the mass couldn't keep up at all, and it almost looked like it was moving opposite to our hand. That's because the phase lag became very large. In our second experiment, we used 2 tuning forks with the same frequency, and we struck one of them, and without touching the other one, it starts vibrating too. And to visually show the vibrations, we have this ping pong ball set up here, and it's going to start bouncing when it vibrates. This is called sympathetic resonance. The sound waves from the first fork travel through the air and push on the second fork. Since they have the same natural frequency, those tiny pushes build up over time and cause it to vibrate. This shows that resonance allows energy to transfer efficiently from one object to another, even without direct contact. Next, we used a whirly tube, which is basically a long tube that makes sound when you spin it. First, I'm going to show you what that looks like, and then I'm going to explain it. As we spun it faster, the pitch didn't change smoothly. It jumped in steps. That's because the air inside the tubes vibrate in specific patterns called harmonics. Each jump in pitch is a different resonant mode of the air column. When we spin it faster, we're forcing more airflow, which can trigger higher modes. This experiment shows us that resonance doesn't just affect motion, it also determines the specific sound we hear. In the last experiment, we vibrated a wire loop and looked for different patterns and how it moved. Instead of moving randomly, the wire formed stable shapes like 2 loops or 3 loops. These are called normal modes, which are the natural ways the system prefers to vibrate. In these patterns, there are specific points called nodes, where the wire doesn't move at all, and sections called lobes, where the motion is the largest. As we changed the frequency, the pattern didn't change smoothly. It jumped between these different modes, creating different numbers of lobes and nodes. This shows that objects don't just vibrate randomly, they follow specific patterns based on resonance. And right here is an example of 4 nodes. And this actually connects to quantum physics in a simple way. In quantum physics, things like electrons can only have certain specific energy levels. They can't just have any amount of energy in between. That's similar to what we see here. The wire can only vibrate in certain patterns, not in between patterns. It kind of jumps from one mode to another, like electrons jump between energy levels. So even though it's a simple experiment, it shows a bigger idea, that in nature, some things only happen in specific steps, not continuously. Overall, all these experiments showed us how resonance works. When something is driven at its natural frequency, energy transfers really efficiently. Even though each setup was different, they all followed the same idea. Systems respond best at specific frequencies, not just any frequency. These experiments helped us understand that motion, sound, and even patterns in physics aren't random. They follow predictable rules based on resonance.